All right, Sarah's unable to make it today, so we have Ben Pitzer up again. He's speaking about robot web applications.
So, code quality. No, I'm just kidding. Web applications. Why do we need robot web applications, other than that it's awesome? I think ROS right now is not very diverse. So you can run it on Linux. We've seen Windows today, maybe a little bit of Mac. We saw Android yesterday, but I think there's a lot more out there. And the web is actually sort of, or, HTML and the web is sort of like a unifying factor. And this is why we looked into this this use case. Web applications have the unique advantage if they run in the browser, you don't need to install anything. Right? So you just open your browser, go to a web page, and you control your robot. And it also taps into a much larger ecosystem that we're dealing with right now. Right now, all you guys that are here, you guys are roboticists, right? So you have a formal background in robotics. You know how to deal with hardware and maybe even deal with Linux and all this stuff. But kids at schools these days, they learn JavaScript as their programming language, or Java, right? So, web applications are the way to access this, whole different types of people. Just as a brief history of what's been going on in this area. So we have seen a very cool talk about ROS Java, which is a native implementation of ROS in Java, and it brings ROS to Android phones. There's a project called ROS Serial that many of you may know that allows to run ROS on Arduino boards, for example, and create a point-to-point connection from those boards to like the real ROS communication system. Something similar is ROS Bridge, and this is something that we also use in our project. That also allows to create a very thin layer for communication, where you can basically use any other system to connect to ROS without implementing a whole communication layer like ROS CPP or ROS Pi. And then on the website, on the web side of things, there's also Web UI, which is a project started by Willow Garage, which allows to create and launch apps for the Peer-2 through a website. And we ourselves, about 2 years ago, started the Remote Lab project, and our goal was to get more people involved using our Peer-2. And the way to go was to create a web interface for people so that they can use our robot in our lab remotely. And what I'm going to talk about today is basically an evolvement of this Remote Lab project, and specifically the web application aspect of this. So if you look at the infrastructure, what do we need to bring robots to the web? On the left side, there's basically what you have right now in the ROS ecosystem. So you have some sort of robot hardware and this big computational graph on ROS nodes, which are drivers and algorithms and all those tools. But those those communication layers or those communication systems in between those nodes, they're not really made for communication through the internet, or even to be able to plug into like a browser in that sense. So that's why we had to build this ROS Bridge system, which actually allowed us to funnel all those different communication streams from ROS into a single, very thin serialized communication that can also deal with all the low bandwidth and low or high latency situations that we have through the internet. And then on the remote client side, we had to build some infrastructure that allowed us to unravel what comes through this ROS Bridge stream, and also that allowed us to program ROS in a way that we're used to, or at least we are used to as a roboticist in Python or C++. But once you have that going, you can actually use a lot of tools that are already out there for web programming to build GUIs using WebGL, which I will show in a minute, and also things like HTML and all those crazy web libraries. So let's talk code a little bit. How can we create a connection to ROS through a web browser? So this assumes a little bit that you've seen a web page So here's a very simple script in JavaScript that would be embedded into a website that actually creates a connection to ROS. And it's really just actually just one line of code, right? So you have create a new node. That node connects, in this case, to localhost, which is, so there's a web ROS bridge running on the localhost system then. And since JavaScript is inherently callback-based, we have to create, or we have to register a callback when this node actually registers and when the connection is established. And then once you have that, you can do fun stuff with it, right? So the first thing that we want to do is obviously publishing and subscribing messages. And this works very similar to ROS CPP. So here in this case, you have an interval. What that means, JavaScript, is basically that this function here gets called every 1,000 milliseconds. Every second, you get a publish event, and just publish the time to a string. And the publisher looks also very similar to ROS CPP or ROSPy. The difference here is that in JavaScript, you don't have to explicitly have types for ROS messages. So you just pass a string, what the type is supposed to be, and you create a JSON object that is sort of arranged in the way that that this type is in ROS. And then ROS Bridge takes care of the rest. So when this data comes to ROS Bridge, it gets unpacked and put into the right message and sent down the pipe to the rest of the ROS world. And similar, the subscriber. So here we just subscribe to the same message type again, just to see if it works. So we assume a string object, and then we plot it out. And so here's how it looks like. The simple code that I just showed. So it connects to ROS Bridge, and yay, we receive its time. So the next thing that we want to do is actually controlling robots through the web. Here's, again, a very simple example how to do that. Here we just use simple buttons, and from those buttons we get some sort of like key message. And what we construct is this JSON object, again, up here. It contains the velocity information. So on up and down, we send a linear velocity, and left and right, we send a rotational velocity. And once again, we just put that into this one single line of code. And our web browser now publishes command velocities, in this case, to the turtle sim. And here's how this looks like. Here, this system actually runs on an iPad, and it's connected to our computer and Turtle Sim. And the interesting part about this is also here, the Turtle Sim is also a web implementation. So in this case, even though there's an iPad and a computer, there's actually no actual ROS node running in C++ or Python. Everything's running through the web browser. So here we have one browser connecting to another browser, which I think is quite exciting. So then we also want to have more complex behavior in the browser, and then ActionLib is the next thing in line to get this. And we also implemented a version of ActionLib in JavaScript to allow that. And again, so it's quite similar to what you're used to in Python or C++. So you create an action client object. You have the same function-based callback behavior. So you wait for the server to come up. You create a goal. You send the goal to the action server, and then you wait for the results to come. And when they come, here in this case, they get printed out. And this is basically the same implementation of the Fibonacci tutorial that's also on the ROS wiki, available in C++ and Python. And here, again, kind of boring, but this is what happens. So the connection gets established. Here in this case, the action server actually runs on a desktop in Python. So we have a browser connecting to a desktop here in this case. So once we have established sort of like this low level of ROS, we want to move on to more high-level functionality. And there's two things that we want to do with our robots. One is we want to visualize them, and we want to control them in a much more sophisticated way than just sending simple keystroke events. So one thing that we had to implement is a TF implementation. This is not, just a warning here, this is not the full-blown TF that you're used to in C++. It's sort of a stripped-down version. It cannot do time travel and so on. So it's much more simplistic. But it does the job. It can subscribe to the TF topics. It gets all of them. And yeah, you can do things like visualization. And to make visualization super simple, we also created a bunch of tools for that. So one is the what we call a visualization manager, which basically creates entire environment like Ogre uses for Arvis. And you can just drop in different topics, different sensor nodes, and visualize them in the web browser. And this is what you see here. So once the node is established, first we need to create a transform listener, and then we just simply create a visualization manager. And that thing actually hooks up to one of the new HTML5 concepts, which is called a canvas. So it's a generic field in HTML that you can draw on. And then we initialize that visualization manager with our node and the TF listener that we just created. And then in this simple example, we just add a grid to visualize. And the grid is supposed to be centered at the ODM combined topic, and it's has the size of 10. That's basically what this is doing. So it's just a few lines of code, and the output is this. So we have an actual 3D rendering in the web browser that uses WebGL. So it's hardware accelerated rendering. And we can visualize 3D data. And the same way we can add grids, we can also, as I mentioned before, add other cool stuff. For example, a robot model. And here we use the exact same techniques that ROS also uses to describe robots. So we use the URDF as a resource for the robot model. And the URDF, as we have heard in the talk, also contains visualization information. So it contains the meshes and all the arrangement of meshes and the textures and so on. And our web visualization can use all of this resources to actually visualize this in the browser as well, the same way Arvis can do. And the second thing that we add here is a point cloud 2. So just from the RGBD camera, the point cloud stream. And here you can see that. So here the turtlebot rendering. So we see the robot model centered on the grid, as well as the point cloud. So as you can already see here, since it's a web environment, we cannot expect to stream point cloud data with 30 frames per second in full resolution. So we have to scale back a little bit for the web. So a technique that we used here was also described today. We compress the point cloud, or we sample the point cloud so it's not as dense anymore using the octree filter. And we also publish it in smaller frequencies. So lastly, what we also want to do here is control the robot. And one really cool tool for doing that, and it hasn't been mentioned well here, is interactive markers. So you have seen markers in Arvis probably for just visualizing points and just any arbitrary marker or shape in Arvis. And interactive markers actually adds interactive capabilities to those markers. So you can actually move them around, and those actions trigger new ROS topics that get sent to a server, and then you can actually use those markers to control your robot. So in this case, the turtlebot actually uses or has a marker server that allows you to steer and control the turtlebot, and we can just drop this in here into a web visualization and drive the robot around using those markers. So you can see those arrows. We can steer forward and backward, and then this fancy ring. You can turn basically. I see it going now, and that turns the robot. So something that's really, really cool about those interactive markers is that once you implement the API and the infrastructure to visualize and interact with them, you have sort of created like a generic way of interacting with robots. So the same way this TurtleBot interactive marker visualization works, the same way we can also interact with a PR2. So no line, we don't need to add anything to our infrastructure to enable this, or to any other interactive marker application, which is really really exciting. So putting this all together, we can really really easily create very complex web applications that allow us to interact with the robot, to visualize certain things. Here you can also see that we plugged in a camera stream, a live camera stream from the camera. And what's not really shown here right now is we can also plug all this stuff into a very nice GUI. We are not really creative designers, but there are certainly people that can do that, and I've seen already very amazing things what people do with this stuff. Just as a note, web is not a local connection. We've heard this before. There are certain limitations to the web, and we have to really make sure that we address those. One thing that we noticed, and we've also heard that before from Tully, is that there's actually quite some overhead in TF, and it creates quite some bandwidth. You'll never notice that if you just work on a local LAN connection, but if you go to the web, it really hurts. And so on the right, so on the top image here, you see actually this red. You can't really read it, but that's basically the traffic generated by TF in kilobytes per second. And this is quite a lot, and you cannot just pump this over the web. So what we created is little helpful packages. In this case, we call it a TF manager. That basically listens to all the TF messages, and it publishes only changes in the TF system. And that really reduces the bandwidth for our web application. And you can see that here. So here is actually an experiment done with a PR2. So only those spikes of the TF message only occur when you actually like move an arm or you start moving the base around. And that really greatly reduced our bandwidth. Another thing that I mentioned before was the PCL filter that really helped to get the bandwidth down. So just some takeaways. We all love ROS and we all love robots. They're awesome, but robots and the web together, that's really awesome. So this infrastructure, ROS.js, that I just mentioned, really allows to really rapidly prototype systems to control robots from any system that supports web browsers. And I mean, there's some caveats to it, like some of the technologies that I've shown, like this WebGL is not supported on all of the browsers yet, but it's just a matter of time. Also, programming robots in JavaScript is super easy. You have seen it. It's just a few lines of code, and you're up. There's a very small boilerplate that you need to do. You don't need to compile anything. You just fire up an editor, you create a web page, and you're done, right? And you don't need a specific operating system to do that. You can do that from anywhere in any system that you want to do it. And it's also very easy to deploy, right? So you just drop your web page somewhere, and you can access it from your iPhone, your computer, and any other system. And just as a takeaway, again, sending large data streams to the browser is a very bad idea. And so if you want to develop anything in this area, really make sure that you know what you're sending to your browser. That's pretty much it. I'm happy to take questions. Here's just a list of the contributors to our project, and also a link to our webpage, where also all the tutorials that I showed today, you can look them up on this webpage. Thank you. So the question was in the example where there was the iPad and the computer, the TurtleSim computer, if there was a ROS core running. Yes, so the ROS core was running on the desktop computer. So there was two things running on the desktop. One was the ROS core, and the other one was ROS bridge to create the connection. So the question was, WebGL support is still pretty sparse on systems. Is there support for just 2D, native 2D rendering? So the answer is no. Right now we don't have any other way of rendering 3D graphics. So the visualization manager that I showed you really relies on WebGL right now. Though the example that I showed with the iPad and the Turtle Sim, and the Turtle Sim was also running on the web browser. And the Turtle Sim in this case was not programmed in WebGL. So that was just using standard canvas elements. And you can do that. It would just be very painful and very slow to render 3D graphics in that way. So, but I think, I mean, we have been monitoring this WebGL development for quite a while now, and it's getting more and more support and traction from browser developers. So I think it's just a matter of time until it gets into all the mobile devices and also all the browsers.
Time for one last question.
The question is Java 3D still around and can that be used? Actually, I don't know if it's still around. When we started this whole project, we looked into two different ways of doing the same thing that we're doing now. And Java 3D was one of the things, O3D and other technologies. But we didn't see real progress in those areas. So I actually don't know. I think WebGL is the way to go. Thank you.